Hello and welcome to the Big Bang Kilonova Hypothesis podcast. I'm Stuart McLean, your host, the progenitor of said hypothesis, and today we're going to be talking about Georges Lemaître and the true genius of Georges Lemaître and in his description of the primeval atom. That's how he calls it, the primeval atom. I probably prefer the term primordial. I think there's probably something a little bit lost in translation in there. But who is Georges Lemaître, if you don't know? Well, he is the granddaddy of the Big Bang Theory. He was the first person originally published the idea in 1927, and it follows on from Einstein's discovery of the equations of general relativity. So by studying the equations of general relativity, what Lemaître found was that given a homogeneous universe and all the galaxies, we see all the galaxies flying away from one another, you realize that if you wind the clock back in time, they all come together from a single point, and this point we now call the Big Bang, though he didn't actually call it as such. But in order to try and present his idea, he needed to think of, well, what's the underlying cause or reason for this to happen? And he put for this idea of the primeval atom. This particular book is an essay on his work, or the book that he wrote, discussing his idea of the primeval atom, and basically described it. It dates from because this is a time of where radiation had just been discovered, and where they discovered the splitting of the atom, which resulted in the Manhattan Project in World War II and the development of the atomic bomb. But back in 1927, they hadn't heard of atomic bombs. But his idea was based around the atoms being split. And imagine this massive big atom, the single beginning atom, the primeval atom, from which split, and then in turn split and split, split and split, and keep splitting until it broke up into hydrogen, into what became the nucleuses of hydrogen atoms. So his description of this one single big atomic nucleus is exactly a description you can give to a neutron star. Neutron star is what is my primary causal mechanism, or two neutron stars in what I call the superverse, our larger parent universe. Two super neutron stars came in, collided and shattered, and the resultant entrapment of space-time of the superverse gave rise to two new entrapped balloon enclosed manifolds of space-time, which are to us our universe. Of course, the full description of what a superverse is and what a subverse is, and what all the primary evidence for the Big Bang Kilonova hypothesis I present in my original film, The Big Bang Kilonova Hypothesis. And in it, I go through. I describe what a superverse is and a subverse is in the context of general relativity by way of looking at the Kerr metric and Penrose diagram, and then from there, right. First, define what a subverse is, i.e. entrapped balloon manifolds of space-time that grow from black holes within our universe, and then further what else we see. And of course, I particularly go on to talk about the cosmic microwave background radiation and the primary evidence that a kilonova is responsible for the creation of our universe, as shown by the cosmic microwave background radiation. But coming back to the idea of the primeval atom, a neutron star essentially is a big, massive atomic nucleus. A small atomic nucleus, like you get in any normal element, is composed of neutrons and protons bound together in a small space. But that space is so small that it really doesn't occupy very much space within an atom. For example, the vast majority of free space within the volume of an atom is mostly free space. So, for example, hydrogen atom has 99.999999999.4% free space. 0.6% volume is actually occupied by the atomic nucleus and the orbiting electron in the hydrogen atom. And essentially, if you had a sugar cube that was purely made of atomic nucleuses, like if you had a sugar cube from a neutron star, the matter of that would be so dense that it would weigh 5 billion tons, the weight of Mount Everest. And a neutron star weighing about 1 to 2 solar masses is probably about 10 to 12 kilometers in width. So they're very small objects, these neutron stars, but very, 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 very densely compacted with neutrons. And the nice thing about neutrons is that they all have the same property they have the same number of quarks bound within them. They have the same mass energy density. They all have the same spin. They all have the same charge, which is neutral, 0. So they're all exactly the same. And when arranged and compacted, well, nature, when it efficiently compacts something into a small volume, uses a crystallized structure, so like an isometric or a cubic lattice structure. So one description of a neutron star is to describe it as a crystallized lattice of neutrons just packed in one against the other. So it is both. So in all the neutrons having the same property, and in having the same number of neutrons in all the directions having the same order, say like a cubic lattice, you have something that is both homogeneous and isotropic. And this is why I think Georges Lemaître used the primeval atom, or just described his idea in the concept of the primeval atom, which split and then split and then split and then split as underwent nuclear fission, as it broke down and gave birth to our universe. That was as far as I know, as far as I can remember, the story goes that he really didn't want to show the conclusion that by taking Einstein's equations of relativity and rewinding the clock back, all the galaxies come together. Before he could I think he really wanted to find the causal mechanism as to how this came about, and how this came about was his idea of the primeval atom, because at the end of the day, an atom composed of, as he imagined it, were neutrons and protons. Actually, I've got some artwork. Let's look at some artwork of how I drew the primeval atom. So here I just tried to describe an atom that has got lots of neutrons and protons in it, but it's of sufficient scale that we can see all those particles. Trying some new. So as we go through the animations here, these are all different variations of trying to picture this primeval atom as Lemaître originally described it. All the protons and neutrons are compacted into one single nucleus. It's all bunched together. Here I'm trying to use different composition techniques, but there's this ordering within. Actually, if I just pause this for a second, one of the things wrong with this particular animation is the mesh of the sphere that I'm using in the render is also grouping together the atoms within inside it. So I'm using a particle system to try and generate all these different particles. Let's see how it goes. As this one forms a bit of an ordering as it progresses. So try a different technique using individual instead of using particles, using more kinematic approach by getting colliding objects in one another. But here you can see inside there's something shifting around, trying to jostle the atom together. Here I actually described what his idea was of the Big Bang, the atom splitting apart. So we start off a big nuclear primeval atom which splits, and then these two in turn go on and split again and again and again and again. So that was my artwork trying to represent this particular idea of the primeval atom. So come back to my browser, and so one of the things I want to start with is I found a review where found this particular article in Science magazine, dating from the 1950. It's a review of Georges Lemaître's book, The Primeval Atom, an essay on cosmology. So let's go through it and read it together. For some 20 years, past Canon Lemaître has been working towards an extremely bold and most exciting theory of cosmology. Of course, it should be noted that Georges Lemaître was Catholic, Belgian Catholic priest. So he was a canon, hence Canon Lemaître. This theory has at its cornerstone the hypothesis that the present physical universe had its origins in a single massive super radioactive atom whose decay products after many generations are to be identified with the material particles and radiation constituting the universe. The spatial-temporal structure of the universe is then the expression of the external relations of this horde of product particles governed by the field equations of the general theory of relativity as developed in the theory of the expanding universe. At each stage in the evolution, the material particles are accordingly subject to an attractive force and to a repulsive force, the former gravitational, more effective at shorter distances, and the latter due to the cosmological constant, more effective at greater distances. The interplay of these two forces brings about the aggregation of matter into stars, of stars into well-defined galaxies, and of galaxies into more loosely organized nebular clusters. Meanwhile, the more vagrant high-energy particles and radiation resulting from the decay are coursing through the finite closed universe as ultra-penetrating cosmic rays. Such is the grand scheme of Lemaître's cosmology. Rather than a finished theory, it is an outline of problems to be attacked, enlivened by most exciting suggestions as to how the answers may be expected to fall out. This is the fare which is offered. This is the fare which is offered the intellectually mature English reader in the present little volume of 5 of Lemaître's papers and addresses. These essays, tied together by an introduction written by the author, represent a spread in time from 1929 to 1945. Although some repetition is thus inevitable, the spread enables the reader to partake voraciously in the evolution of the theory. The more technical aspects of the subject are for the most part only alluded to in passing, but the technical expert will find the mathematical backbone of the hypothesis, the theory of the expanding universe, most elegantly presented in an appendix. The more philosophical implications of the effort are touched upon in a preface by Ferdinand Gonsenth, excuse my butchering of the name, and its relation to astronomical fact in a brief foreword to the English edition by Henry Norris Russell. The translators, recognizing that translation involves a compromise between transliteration of the author's words and conveyance of the author's meaning, having consciously leaned heavily towards the former, with the result that in some cases the author's meaning has been somewhat obscured by too literal translation. Let no one be misled by the author's distinguished position in the Church to expect to find therein raison d'etre for his cosmology. I'll comment on that in a second. Its formulation is a truly scientific venture, which is to stand or to fall on its ability to measure up to the facts in accordance with accepted scientific methodology. The general reader will find intellectual stimulation in the splendid account of the hypothesis of the primeval atom, and the technically expert among them may well be incited to accept the challenges to test the hypothesis where it impinges upon his own field. Of course, as we know nowadays, the Big Bang theory itself is the accepted theory of how our universe is born. How and why it came to be is what's in contention. The main proponent that exists at the moment is inflation theory. Big Bang Kilonova hypothesis is the counter to it. So essentially, if you're going to put two hypotheses in the ring, it's inflation theory on one side, Big Bang Kilonova hypothesis on the other. Mine, as we discussed in the last episode, uses the Philosopher's Stone, a kilonova, because kilonovas produce gold, as And that is an observable fact, as we discussed in my last episode, where we looked at that article from Harvard University. Namely, we see the light from the kilonova, put it through spectral analysis, and we see the signature of gold. It's where gold comes from. A kilonova is the philosopher's stone. Of course, Lemaître probably didn't quite have to deal with a grail, the evidence of which I talk about here in quite good length, and then an account of all the weird things I sort of followed on from it. I would have loved to have shown him the grail. It's so beautiful. This particular structure is the subject of my next film. These were the subject of my last. This one. But returning back to some kind of sanity, science for me is my comfort zone. Outside, getting into religiousness and spirituality, that I like science because it's clean cut. I don't know. It's my way of seeing the world, and it's proven to be one that produces the greatest number of applications. Applications are extremely useful. I like to be an inventor. Okay, so the other thing I want to particularly go through is actually Lemaître, to read through an editorial note about Lemaître's original paper. So Lemaître's original paper, I've got a snapshot of it here. A homogeneous universe of constant mass and increasing radius, accounting for the radial velocity of extra-galactic nebulae. Of course, the reason why it is a homogeneous universe is because, one, when we look out into the universe, we see galaxies at different ends of the universe. Both have the same shape, structure, have stars. Those stars have the same elements in them. They all operate under the same universal laws of physics as we know them. Though, when you think about what exactly the universal laws of physics are in the superverse or in the subverse, I'm still working that one through. Here's a good question. Here's a question that's really sort of like trying to gnaw away at me. The speed of light in our universe is 3 times 10 to the 8 meters per second. What's the speed of light in the superverse? Or let me rephrase that. A particle of light gets emitted across and travels across the electromagnetic field of the superverse. The electromagnetic field has been ripped apart and ballooned up into 2 separate balloon universes, one being our universe, the other one being the universe of antimatter. They are formed from the shell of the electromagnetic field of the superverse. But the electromagnetic field of the superverse is like the electromagnetic field, and it has a particle of force on it, that being a superphoton. So what's the speed of travel of a superphoton across the fabric of the superverse? And vice versa, for a subverse in our universe. What is the speed of light of a photon across its electromagnetic field? That's a question that if you've got an answer, put it down in the comments. There's probably a Nobel Prize in it as well. and a whole new outlook on the whole universe and everything. But for the meantime, let's have a look at this editorial note about Lemaitres' original paper. So this is done by Jean-Pierre Luminet. Marseille. I'm sorry, I'm just pausing for a second because I think there's another Jean-Pierre Petit who came up with Jean-Pierre Petit. He came up with a rather interesting cosmological model based on the logic of charge power to time symmetry. But the person who originally came up with that is Andrea Sakharov. I think he was from Marseille as well, but I'm not sure. I just want to. Oh dear, I've got a broken link. I'll have to fix that to my webpage. Let's just look at Janus cosmological model. Hey. So he called it Janus after the two-faced gods of the Roman pantheon. So yeah, Jean-Pierre Petit. Yeah, so he came up with the Janus cosmological model. But it's so yes, but I was trying to see if he was from Marseille. Many broken links. Yes, Jean-Pierre Petit, Marseille. So, small world. But this is Jean-Pierre Luminet from Marseille as well. So, let's go through this. A homogeneous universe of constant mass and increasing radius, accounting for the radial velocity of extra-galactic nebulae. Jean-Pierre Petit Luminet. On introduction, as already pointed out in a previous Golden Oldie, devoted to Lemaître's short note of 1931, which can be considered as a true charter of the modern Big Bang theory. Although the Belgian scientist was primarily a remarkable mathematician and a theoretical physicist, he stayed closely related to astronomy all his life, and always felt the need for confronting the observational data and the general relativity theory. This basic fact explains why as soon as 1927, while still a beginner in cosmology, he was the first one to be able to understand the recent observations on the recession velocities of galaxies as a natural consequence of dynamical cosmological solutions of Einstein's field equations. Before examining in detail the concepts of his outstanding article, let us summarize the road which, in the few preceding years, led to the young Lemaitre to the expanding universe. In 1923, the same year as he was ordained as a priest, Georges Lemaître obtained a 3-year fellowship from the Belgian government, enabling him to study abroad. He spent the first year at the University of Cambridge, England, where he studied stellar astronomy, relativistic cosmology, and numerical analysis under the direction of Arthur Eddington. Didn't know about that one. He spent the second year at Harvard College Observatory in Cambridge, Massachusetts, directed by Harold Shapley. Harold Shapley, I think that name's familiar somewhere, who worked on the problems of nebula. Then he passed to the Massachusetts Institute of Technology, where Edwin Hubble and Vester Slipher were active. So that's where we. So it was Edwin Hubble that showed Einstein the actual nature of the galaxies flying apart from each other. But of course, so I didn't know he actually went to both Cambridge and then at MIT. And I think Vester Slipher was one of the first people who was really working on finding a solution for the equations of general relativity. While following closely the experimental work, let's just look up Vester Slipher, because I recognize the name. I'm just trying to place him where he is. Vester Slipher was an American astronomer who performed the first measurements of radial velocities for galaxies. He was the first to discover that distant galaxies are redshifted, and thus providing the first empirical basis for the expansion of the universe. So that's where I recognize his name, because if I go back to my piece, I think I very specifically I mentioned Vester Slipher in there when I was doing it. Anyway, so yeah, Vester Slipher, he basically discovered that galaxies are moving away from us, and thus hence how Lemaître came to be working on this. While following closely the experimental work of the American astronomers who were going soon to found observational cosmology, Lemaître undertook a PhD thesis at MIT with his compatriot Paul Hindmans as advisor on the gravitational field of fluids in general relativity, a theoretical subject suggested by Eddington. Now, the equations that describe the motion of a perfect fluid are themselves supposed to be an exact solution of the equations of general relativity. So I thought that was a fairly, so as you see, I'm learning as I go here. It's always a learning curve in cosmology, and I really have got a massive amount of imposter syndrome. But I'm the only guy thinking about it in terms of a kilonova. So hey, that's how you become a cosmologist. Just accidentally walk into it. At the end of 1924, he attended a meeting in Washington, which remained famous since the discovery of Cepheids in spiral nebula was announced, where thereby Edwin Hubble. Okay, sorry. Let me get my pace back. At the end of 1924, he attended a meeting in Washington, which remained famous since the discovery of Cepheids in spiral nebula was announced, thereby Edwin Hubble. This made it possible to prove the existence of galaxies external to ours, and Lemaître understood at once that this new design of island universes would have drastic consequences for the theories of relativistic cosmology. So essentially, before that moment in time, the vast majority, everyone thought that the expanse of the universe was the Milky Way galaxy. The idea of there being other galaxies external to us was unknown. And it comes down to, I think it's what's used here as Cepheids. I think it's variable stars that allow you to get a precise measurement of distance. A Cepheid variable is a type of star that pulsates radially, varying in both diameter and temperature, producing changes in brightness with a well-defined stable period and amplitude. A strong direct relationship between Cepheid variables, luminosity, pulsation periods, establish Cepheids as important indicators or cosmic benchmarks for scaling galactic and extragalactic distances. This robust characteristic, or classic Cepheids, was discovered in 1908 by Henrietta Swan Leavitt, was an American cosmologist, a graduate of Randolph College. She worked at the Harvard College Observatory as a computer, so someone who just does calculations, just wrote calculations before the concept of actually doing it electronically, where it was all done manually, pen and paper. With examining photographic plates in order to measure and catalogue the brightness of stars. I remember a documentary I think I saw about her. So we owe her a great debt of gratitude for her work after studying thousands of variable stars in the magnetic clouds. So, coming back to the art. So yeah. So essentially, at this particular conference, we discover using Cepheids. We see that these structures, these faint fuzzy blobs, as they were then in the telescope, were actually galaxies. Though with the development of the observatory that Edwin Hubble had, that they became less blurry, and you can actually see that they were composed of millions and millions and millions of stars. And so you realize that we live in one of these structures called a galaxy, and these other external objects are called galaxies. Until that point, the Milky Way galaxy was our universe. So this is a very important leap in sense of human thought. That's why I love cosmology. It's and effectively these island universes, as it's quoted, which we now call galaxies. On July 1925, his American stay ended, and Lemaître had to go back to Belgium. In the same decisive year for observational cosmology, Lemaître obtained his first notable scientific results concerning the cosmological solution found by De Sitter. So let's look up De Sitter, because again, this is a name I keeps resonating throughout cosmology. The main application of De Sitter space is use of general relativity, where it serves as one of the simplest mathematical models of the universe, consistent with the observational accelerating expansion of the universe. More specifically, De Sitter space is the maximally symmetric vacuum solution of Einstein's field equations with a positive cosmological constant corresponding to a positive vacuum energy density and negative pressure. There is cosmological evidence that the universe itself is asymptotically de Sitter, i.e., it will evolve like the De Sitter universe in the far future when dark energy dominates. Dark energy comes into our universe because it is mass energy density outside the volume of our trapped manifold of space-time, around which our universe flows. So when I say flow, let's have a look at some evidence of it flowing around some voids. Specifically, I refer to yes, here we are. So this is it flowing This is actual observational evidence of our galaxy flowing around the local supervoid, or the local void, as done by R. Brent Tully, who's mapped out the far side of the Milky Way galaxy in order to produce these maps. And the flow of the galaxy, or flow of all the galaxies around the local void. See, all pointing in the same direction, Whereas the Lambda CDM model says it should disperse, it should go out, it should inflate like bread cooking in the oven. An air pocket develops inside the dough of the bread and expands evenly. So all the galaxies should be moving out away evenly. But here we see it flowing around. Here we have our Milky Way galaxy. It's flowing around the local void. This is actually called dark flow in cosmology. So let me just type dark flow. So the explanation for this is this dark flow. Essentially, our universe is expanding into the volume of the superverse, which is mostly flat. It's all mostly flat, hence the cosmological constant is flat. It uses a flat tensor. It's an identity. But coming back to the article, so sorry for the slight tangent off from there, but just wanted to show what Decision Space was. On July 1925, its American stay ended, and Lemaître had to go back to Belgium. In this decisive year for observational cosmology, Lemaître obtained his first notable scientific results concerning the cosmological solution found by De Sitter. In this first article, he demonstrated how he could introduce new coordinates for the De Sitter universe, which made the metric no more static, with a space of zero curvature and a scale factor depending exponentially on time. This metric would be used 20 years later by the keenest adversaries of the theory of the expanding universe in the framework of steady-state models, and still later in the 1980s to describe the hypothetical inflationary period of the very early universe. So the whole idea of inflation is to describe how these large cosmic voids came to exist. As we just saw, it flows around the void. Doesn't move, instead of moving away like that. In the second article, he deduced that the relationship between the relative speed of test particles and their mutual distances in the De Sitter universe was linear. It was the first time that the cosmological constant, when it is positive, was seen allocating the role of cosmic repulsion, forcing the world lines of particles to recede with time. However, although he found this non-static feature to be promising because of its connection to the redshifts of nebulae, he also realized that the model resulted in an infinite Euclidean space that he considered inadmissible as a neo-Thomson. He did not accept the actual infinite and remained faithful to the finitude of space and matter throughout his career. Thus, he had to seek for an alternative explanation involving a truly non-static and spatially closed solution of Einstein's equations. So essentially, if we go, let's look at the general equations of relativity. So to give a more meaning to what's actually being spoken about here. So here's one formulation of Einstein's equations of general relativity without the lambda, without the cosmological constant. There's two formulations to it. There's this version, and where it doesn't have lambda, and then this version which does have lambda. So this is this repulsive force that causes the universe to expand. And Einstein put this back into his theory of general relativity in order to describe the steady state model, i.e. the eternal universe, because he didn't believe that galaxies were flying apart from one another. It took Edwin Hubble to actually convince him that the universe itself is expanding, and for a time he called this his greatest mistake, and then so he changed it back to this. But this has come back into fashion because of dark energy. And the lambda here is describing the expansion of the universe because of dark energy coming into our universe. I won't try and describe it in terms of inflation theory because other people can do that. But essentially, it is the lambda in the lambda CDM being cold dark matter, the lambda CDM model of cosmology, which is called the standard model of cosmology. And the lambda in it is representative of the existence of dark energy within our universe. But as I try to demonstrate, well, no, this is mass energy density that belongs to the superverse. It is external to our universe. Our universe is flowing around it like a stone in a river. It flows around it. And the reason there is no dark energy at the time of the Big Bang, as represented by WMAP, actually let's get the pie graph. We'll get the pie graph. Contents of the universe. So this is the actual composition of it today, but there's two images that go together. That's the one. So as you can see, referencing NASA here, this is the WMAP. So this is actually measured. So this is the observational, and in it there is no dark matter at the time of the last scattering of the microwave background sky, or the time when the photons that come from the microwave background radiation began to traverse across the universe as it cooled down enough such that electrons could bind to protons, and then thus the universe went from being an opaque plasma to becoming translucent. And at that time, it was composed of 10% neutrinos, 15% photons, 12% atoms, and 63% dark energy. This particular expanse is I'll cover in another episode because that's a particular subject of the film that I'm building up. But dark energy, as we see it today, composes 72% of the universe as we know it. So, and that's because our universe, our entrapped manifold of space-time, is expanding out into the greater volume of the superverse. In talking about dark energy and how it comes into our universe, I've got a series of animations that show this principle. So in talking about the Boretti supervoid, I talk about it as being a star of the superverse. The size of the star itself is so large that it's 330 million light years across, the Boretti supervoid. So I'm talking about a star that's 330 million light years across. It's a difference of scale. Fractal geometry is a cosmological principle, thus self-similar patterns repeat irrespective of scale. And here is a star of the superverse. In talking about the universe flowing around the volume of the star of the superverse, I have this animation showing water flowing around the volume of a star. So we can see, so it essentially shows how our galaxy, how the Boretti's void came to be inside our galaxy as our universe flowed around it. In talking about subverses, we have these two Fermi gamma ray bubbles of that are in the voids in the northern and southern polar regions of our Milky Way galaxy. In talking about a subverse, I talk about it being an entrapped manifold space-time, both to the north and to the south of the Milky Way galaxy. So here is a subverse inside our own universe, just as our universe is inside the volume of the superverse. So it all comes down to essentially entrapped wormholes inside the rotating black hole. So here's a close-up of it, and then a close-up of the Fermi balls as we see them from the Fermi telescope. In saying what dark matter is, I say it is matter entrapped inside these manifolds of space-time, and thus I'll just back up again. So, and I'm talking about dark energy. Dark energy is matter outside the volume of our universe, belonging to the superverse. Our universe expands into the volume of the superverse. So the reason why space is mostly flat is because our universe, as it expands into the volume of the superverse, which itself is most like an interstellar void, and thus is flat. It only gets deformed and as it has to move around existing objects inside the superverse. So that's what this particular animation shows. It shows the superverse, and it shows our universe growing inside the superverse as two entrapped manifolds of space-time. The galaxies enter and form into the... Finally, with this description... Okay. I'm just wondering which one is that. Finally, with this description now given. And here, this particular animation is showing the recursive nature of, we go through a black hole, through its wormhole, out through its white hole, and out into the new universe, which is inside the parent universe, or the parent superverse. And again, a galaxy inside this universe, we go and fall inside the black hole of that universe, that entrapped manifold of space-time, travelling through the wormhole, the ringularity, out through the rotational white hole, and back out into the subverse. And so it shows the recursive nature of the Big Bang Kilonova hypothesis in its more or less totality. of how one universe comes to be inside another, inside another, inside another. Sort of like very much like a Russian doll. One is inside the other, one's inside the other. So let's return back to going through reading the article. We're reviewing Lemaître's initial paper, or the editorial review of it. So yeah, we're discussing the history of Lemaître, and how he ended up with the ideas such that he could formulate his idea of the primeval atom, or essentially a large neutron star. In 1926-27, Lemaître went again to the United States, where he remained at MIT during 3/4 of the academic year. Back in Europe, in June 1927, he was informed by letter that he got his PhD, having been accepted of oral defense. The same year he was appointed professor at the University of Louvain and published his great article on the expanding universe. 2. Recession of galaxies and expanding universe. Since 1912, Vestus Slifer had undertaken a program of measurement of the radial velocities of spiral nebulae. Interpreted in terms of the Doppler effect, the shifts in a frequency or wavelength implied a radial speed of displacement of the source compared to the observer. Radial speeds were thus indirectly measured by spectroscopy. By 1917, Slifer had analyzed the spectra of 25 spiral nebulae, which he had observed at Lowell's Observatory in Flagstaff, Arizona. 21 of them presented redshifts that could be interpreted as a systematic motion of recession. The exceptions were M81 and 3 galaxies from the local group. However, nobody's expected yet the repercussions that these preliminary data would have soon for the whole of cosmology, mainly due to the fact that the debate on whether spiral nebulae were island universes went on. The evidence for the redshifts mounted, mainly due to Slifer's efforts, and by 1923 reached a score of 36 among 41 spiral nebulae. So the first thing to note here is the word spiral nebula, because when looking through telescopes from the 1923, from the early 1900s, Lowell Observatory was probably the best at the time, and we weren't sure what these structures were. We thought they were nebula, being interstellar masses of gas, like the Horsehead Nebula, the Crab Nebula. But these were different. These look to have they're composed of millions and millions and millions of stars, as we've come to discover as we built better and better and better telescopes over the course of the last century. But back then, they were still thinking, what are these structures? Are they actual distant island universes that we have come to call galaxies, like the Milky Way galaxy, like the Andromeda galaxy? Or are they actually interstellar formations of gas within the actual Milky Way galaxy itself? No, they're actual galaxies that are very far away. And this is coming from what is effectively being termed redshift. You see so if I go back to here, so as galaxies or stars move, the further they move away from us, the greater the distance. And because there is this expansion in space-time from when the photon initially was emitted to the time when it reaches the telescope mirror. This expansion in spacetime causes an expansion in the wavelength of the photon. And this expansion in the wavelength of the photon adjusts it down towards the red end of the spectrum. Hence we say that these bands are redshifted to the red end of the spectrum. Continue on. Slipher never published his final list, but it was given in Arthur Eddington's book of 1923, who noticed that one of the most perplexing problems in cosmology is the great speed of spiral nebulae. Their radial velocities average about 600 kilometers per second, and there is great preponderance of velocities of recession from the solar system. The influential British astronomer suggested that effects due to the curvature of space-time could be looked for and referred to de Sitter's model for a possible explanation. Thanks to his various stays at Cambridge, England, and at MIT, where he met Slipher personally, Lemaître was perfectly informed of these preliminary results, and he wanted to take account of the available data by using a new cosmological solution of Einstein's equations. As the title of his 1927 article clearly states, Lemaître was able to connect the expansion of space arriving naturally from the non-statical cosmological solutions of general relativity with the observations of the recession of velocities of extra-galactic nebulae. He begins to review the dilemma between the de Sitter and Einstein universe models. So, de Sitter model is the one that shows an expanding universe, and Einstein's model was the steady state, the eternal universe. The universe has always been here. The universe has always existed. The de Sitter model ignored the existence of matter. However, it emphasized the recession velocities of spiral nebulae as a simple consequence of the gravitational field. Einstein's solutions allowed for the presence of matter and led to a relation between matter density and the radius of the space, assumed to be a positive curvature hypersphere, being strictly static due to an adjustment of the cosmological constant. It could not, however, explain the recession of the galaxies. Lemaître thus looks for a new solution of the relativistic equations, combining the advantages of the Einstein and de Sitter models without their inconveniences, i.e., having a material content and explaining at the same time the recession velocities. So here we're getting more into the geometry and topology of the mathematics of general relativity in deriving what essentially becomes to be known as the FLWR metric, the Friedman, Walker, Lemaître, Robertson metric. So this is Lemaître's formulation of this particular metric, which was independently done by Friedman, Walker, and Robertson. For this, in the next section, he assumes a positive curved space as made precise in a footnote with elliptical topology, namely that of the projective space P3 obtained by identification of antipodal points of the simply connected hypersphere S3 with the radius of curvature R and consequently the matter density ρ being a function of time and a non-zero cosmological constant lambda. I'm trying to think of an English interpretation of what all that really means. Positive curvature. I think it's the idea that you got mass, and that attracts. Whereas with dark matter, it is a repulsive force, and that repulsive force causes an anti-gravitational gradient away. So positive curvature, I think that's the best description of positive curvature I can probably give. But essentially, it's linking up the bits of topology into a sphere of a given radius that is expanding outwards. That expansion being a function of time, and a non-zero cosmological constant. From Einstein's field equations, he obtained differential equations 2 and 3. I'm just scrolling through to see equations 2 and 3. Okay, not seeing them. For one for the radius as a function of time, and one as a function of density with time, almost identical to those previously obtained by Friedmann. At the time, Lemaître was not aware of Friedmann's work, see below. So yeah, Friedmann independently came up with the same conclusions, or same function of a radius of the universe, the size of the hypersphere, that of the S3 hypersphere of the expanding universe, as both a function of the radius in terms of time and as both of density in terms of time. The difference is that Lemaître supposes the conservation of energy. This is the first introduction of thermodynamics in relativistic cosmology, and he includes the pressure of radiation as well as the term of matter density into the stress-energy tensor. He rightly considers the matter pressure to be negligible. So, effectively, and this is easier in English, effectively, as the universe goes back to the time of the Big Bang, it became a hot single ball of plasma. Effectively, it was like a massive star. From the point of view of the Big Bang Kilonova hypothesis, all this energy came about from the Kilonova explosion being funneled into the entrapped surface of space, manifold of space-time, that inflated into becoming our universe. All the hot energy matter from the Kilonova explosion goes into the balloon universe, and it inflates that balloon up and out. And so this is the thermodynamic consideration, because this cools down and cools down. Now the interesting thing here is entropy, and the second law of thermodynamics, because this is how I approach it. Entropy leads to disorder. It takes a system that is ordered and moves to a state of disorder. This is the arrow of time. It's the unidirectional arrow of time. As fractal geometry and chaos mathematics arise from the complexity of nonlinear dynamics, thus order is created from disorder through chaos and through the field of mathematics known as chaos and fractal geometry. So that's how I'm approaching the whole concept of thermodynamics in my cosmological model. Lemaître emphasizes the importance of radiation pressure in the first stages of the cosmic expansion. Now, it is well known that within the framework of Big Bang models, the approximation of zero pressure is valid only for time posterior to the Big Bang, for approximately 400,000 years. Just like Einstein and de Sitter, Friedman had made the assumption that the term of pressure in the stress energy tensor was always zero. The equations derived by Lemaître are thus more general and realistic because they take into account the second law of thermodynamics. And creates pressure on the sphere, and the sphere grows because of the heat and energy as it cools down and dissipates. It creates the pressure and inflates the bubble. Lemaître shows how the Einstein and de Sitter models are particular solutions of the general equations. Next, he chooses an initial condition, r prime equal to r prime. So I presume these are differentials. So the acceleration is 0, the velocity is 0, r equals r0 at time equal to minus infinity. So essentially, this is what's being plotted down on this graph. So, figure 1. The 1927 Lemaître's universe model, later named Editorial, the radius r0 of the static Einstein hypersphere is reached asymmetrically for t equal to minus infinity. The origin of cosmic time is arbitrary, thus the model does not pose any problems of age. So essentially, as we reverse time, we find that the universe shrinks and shrinks down to the point equal to r0. So that's what this initial model is, that Lemaître has put together, shows. As a consequence, the exact solution he obtained in equation 30, where are these equations? So, unfortunately, we're not seeing the actual equations being shown or being discussed. As a consequence, the exact solution he obtained in equation 30 describes a monotonous expanding universe, which one indefinitely goes back in time, approaches in an asymmetric way the Einstein static solution, while in the future it approaches asymptomatically an exponentially expanding de Sitter universe. So Einstein's static solution is his static model of the universe that has always been here, whereas the de Sitter model is the one that describes the expanding universe. This model derived of initial singularity and of consequently not possessing a definitive age, as well as the monotonous solution of second species found earlier by Friedman, will be later baptized the Editorial-Lemaître model. Lemaître does not provide a graph for RT, but gives numerical values in a table from t equal minus infinity to plus infinity. For the clarity of our figure 1 depicts such a graph. So we've got figure 2, which actually is Lemaître's. So this is actually published in 1998. But these graphs were Lemaître's graphs of his plots of these model universes, looking at various conditions of how it would expand out. So, handwritten graph by Lemaitre. This extraordinary diagram plotted by Lemaitre in 1927, but unpublished until 1998, depicts the time evolution of the radius of the universe with the cosmological constant, denoted A, for a space of positive curvature. All the models start with a singularity in x equals 0, t equals 0. For a sufficiently large cosmological constant A, the universe becomes open. The most recent cosmological data are compatible with a Lemaitre solution with positive curvature and accelerated expansion. Top curve. So the top curve is the one that most closely fits what is actually observed, from what I can gather there. Lemaitre conceived the static Einstein universe as a kind of pre-universe, out of which the expansion had grown as a result of an instability. As a physical cause for the expansion, he suggested the radiation pressure itself, due to its infinite accumulation in a closed static universe. But he did not develop this erroneous idea? It's erroneous in the static part, but measurements of the cosmic microwave background do show that we are possibly living in both a flat and enclosed universe. Let me find those particular papers for you, so I can. CMB Cold Spot, I think, is probably the most likely one. Let's see. Look for the word flat. Oh, we'll get there. A flat universe. So a flat. So this is actual observed measurements from the cosmic microwave background, showing that we live inside a flat universe. So it's flat because it's expanding into the flat superverse, or the flat space of the superverse, surrounding superverse. And let's find the enclosed, but I also say it's enclosed. I think it's probably more in the general relativity. Actually, the keyword would be closed. Closed. Bear with me. CME data showing a positive curvature. Which one's that? Yes. So here's the paper that I reference in terms of saying our universe is an entrapped manifold of space-time, so it is closed, as shown from evidence from the Planck from the Planck satellite mission, which mapped the microwave background radiation. And we also live as it expands into a flat universe. So when I say closed and flat universe and trapped manifold of space-time, this is the evidence that I'm pointing to, the primary microwave evidence I'm pointing to in terms of showing the validity of my argument. But where were we? So Lemaitre conceived the static Einstein universe as a kind of pre-universe, out of which the expansion had grown as a result of an instability. As a physical cause for this expansion, he suggested the radiation pressure itself, due to its infinite accumulation in a closed static universe. But he did not develop this erroneous idea. While giving preference to this particular model in his article, Lemaître nevertheless calculated separately the whole of dynamic homogeneous cosmological solutions, since he had the general formula, equation 11, making it possible to calculate the time evolution of all the homogeneous isotropic models with positive curvature. The Lemaître archives at the University of Louvain keep a red pad with the inscription 1927, which contains the gallery proofs of his article, some notes and handwriting connected with the paper, and 2 diagrams, which unfortunately do not appear in any of his publications. These diagrams depict the time evolution of the space scale factor depending on the value of the cosmological constant for all homogeneous and isotropic solutions of Einstein's equations with positive curvature of space. i.e., this graph here. As mentioned above, the 1927 article does not refer to the work of Friedmann, published in the physics publication for Germany at the time. I will not try and butcher the name. Although it wasn't one of the best known journals in theoretical physics at the time. It's one I think which Einstein published, and this absence seems strange if one remembers the 2 notes by Einstein's publication in the same review, which had been largely discussed in the scientific community. A plausible explanation is that Lemaître could not read the German. Friedmann's articles were pointed out to Lemaître by Einstein himself during their meeting at the 1927 Solvay conference. The reference to Friedmann thus appears for the first time in a text of 1929 written in French, Le Grand Délai de Passe, in which Lemaître thanks Mr. Einstein for the kindness that he showed by announcing to me the important work of Friedmann, which includes several of the results contained in my note on a homogeneous universe. The reference will also appear in the 1931 English translation of Lemaître's article, see below. The exceptional interest of Lemaître's work is to provide the first interpretation of cosmological redshifts as a natural effect of the expansion of the universe within the framework of general relativity, instead of a real motion of galaxies, as it is written down in equation 23. Space is constantly expanding and consequently increases the apparent separation between galaxies. This idea will prove to be one of the most profound discoveries of our time. It is. Because the more we've observed the universe, after a century of observation, this is the story that we are seeing. This is why the Big Bang model is considered by the vast majority of cosmologists to be the explanation for how the universe was born. Of course, in the steady state model, the universe isn't born. It has always existed. Where are we? The exceptional interest in Lemaître's work is to provide the first interpretation of cosmological redshift as a natural effect of the expansion of the universe within the framework of general relativity, instead of a real motion of galaxies as it is written down in equation 23. Space is constantly expanding and consequently increasing the apparent separation between galaxies as it expands. This idea will prove to be one of the most profound discoveries of our time. The relation of proportionality between the recession velocity and the distance is an approximation valid at not too large distances, which can be used within the limits of the visible spectrum. Then, using the available astronomical data, Lemaître provides the explicit relation of proportionality in equation 24 with a factor of 625 or 775 kilometers per second per megaparsecs. What would later be called the Hubble constant is really actually Lemaître is really the person that came up with it. Depending on his choice of observations which presented an erroneous scatter. This is the first determination of the so-called Hubble law and the Hubble constant that should as well be named Lemaître's law. For this, the Belgian scientist used a list of 42 radial velocities compiled by Gustav Strömberg, a Swedish astronomer at the Mount Wilson Observatory, and deduces their distance from a recent empirical formula between the distance and the absolute magnitude provided by Hubble, who himself took them from Hopman. Eventually, Lemaître is able to give the numerical figures for the initial and present-day values of the radius of the universe, R0 being 2 to... So we've got some initial figures for our model universe. At the very end, he points out that the largest part of the universe will be forever out of reach of the visible spectrum, since the maximum distance reached by the Mount Wilson telescope is only r divided by 120, whereas for a distance only greater than r over 11, 5 the whole visible spectrum is displaced into the infrared. He could not imagine the space era with infrared and sub-millimeter telescopes, microwave telescopes, placed on board of satellites. So essentially here we're talking about what was known at the time from the Mount Wilson Observatory that Edwin Hubble... No, I think did he build it? I guess we're going to look that up. But essentially what I think what this is saying is by looking at Lemaître's models and initial calculations of the initial radius, they tried to work out what is the actual size of the universe as a whole. But since then, we've developed better and better telescopes, and then even satellite telescopes out in space, so ones that can actually see the microwave background radiation. We have seen above that Lemaître knew already all the solutions of Einstein's equations for homogeneous and isotropic universes. The reason why he privileged a very particular model adjusting the cosmological constant in order to have no beginning of time is due to his overestimate of the Hubble constant. As is well known, the latter gives an order of magnitude of the duration of the expansion phase, with the estimate of about 600 kilometers per megaparsec found by Lemaître. This period of about 1 billion years only, a number less than the age of the Earth, estimated by geologists all the time. Thus, the model with exponential expansion and no beginning allowed to reconcile the theory with both astronomical and geological data. So one thing that stands out to me is this period of about 1 billion years only, a number less than the age of the Earth, estimated by geologists of the time. I was trying to think about that one because First reactions. The significance of Lemaître's work has remained mostly unnoticed for 3 years, not exclusively, but partly due to the fact that it was published in French in an obscure and completely inaccessible journal, as is sometimes claimed, instead of one of the prestigious astronomical journals of the time. Of course, remember the author is from Marseille. As rightly pointed out by Lambert, the Annuals de la Société Scientifique de Brussels, scientific publication for Brussels, the Annuals of which published some articles in English, had an excellent scientific level and therefore were displayed in a large number of academic libraries and observatories all around the world. Also, French could be read by a much larger scientific audience than today. Indeed, the main obstacle to a larger diffusion of Lemaître's article was that most of the physicists of the time, such as Einstein and Hubble, could not accept the idea of a non-static universe. This was not the case with Eddington. Unfortunately, his former mentor, to whom Lemaître had sent a copy, either forgot to read it in time, or he had not understood its importance. So I did find it, I'm thinking about it, Hubble was more believing in a steady state model rather than what Lemaître was trying to actually show as an expanding universe. From the 24th to the 29th of October 1927, the 5th Solvay Conference in Physics took place in Brussels, one of the great meetings of world science. The Solvay Conference was devoted to the new discipline of quantum mechanics, whose problems disturbed many physicists. Among them was Einstein. For Lemaître, it was the opportunity to discuss with the father of general relativity. He later reported himself on this meeting. While walking in the alleys of Parc Leopold, Einstein spoke to me about an article little noticed, which I had written the previous year on the expansion of the universe, and which a friend had made him read. After some favorable technical remarks, he concluded by saying that from the physical point of view, that appeared completely abominable to him. After some favorable technical remarks, he concluded by saying that from the physical point of view, that appeared completely abominable to him. I think the idea that the universe is expanding rather than being in an eternal steady state. As I sought to prolong the conversation, Auguste Piccard, who accompanied him, invited me to go up by taxi with Einstein, who was to visit his laboratory at the University of Brussels. In the taxi, I spoke about the speeds of nebulae, and I had the impression that Einstein was hardly aware of the astronomical facts. At the university, everyone began to speak in German. Einstein's response to Lemaître shows the same unwillingness to change his position that characterized his former response to Friedman. He accepted the mathematics, but not a physically expanding universe. Now, reading that, I'm just remembering another interpretation that I heard about it. I think Einstein had done the mathematics, and his mathematical and basically his mathematics had shown that it was going to be a steady state universe as opposed to an expanding one. But Einstein made a mistake in his tensor calculation, which a more experienced, I think maybe even Friedman might have, yeah, I think it's probably Friedman that pointed it out to Einstein that he made this mistake in the tensor calculation, and so later on he came to understand that Lemaître was actually right mathematically, that the universe is expanding, which is as a consequence of Einstein's theory of general relativity. Moving on. In 1928, H.P. Robertson published an article in which he wanted to replace de Sitter metric by a mathematically equivalent in which many of the apparent paradoxes inherent in de Sitter solution were eliminated. He got the formula V equals CD over R, where D is the distance of the nebula and R is the curvature of the universe, but in the framework of a static solution. Robertson used the same set of observations as had taken by Lemaître, and that would be taken by Hubble 1 year later. From this, he calculated R equals 2 times 10 to the power 27 centimeters, and a proportionality constant of 464 kilometers per second per megaparsec. That he did not calculate. The figure can be found in 31. So the FLWR of the FLWR metric, the R in it being Robertson. So this is where he's also coming into the picture. So mathematical equivalent in many of the apparent, so essentially sort of tidying up the mathematics such that it gets rid of the paradoxes, but he's doing it in the context of a static solution. So Robertson used the same set of observations as had been taken by Lemaître, and that would be taken by Hubble 1 year later. The main interest of Robertson's work is that he was the first to search in detail for all the mathematical models satisfying a spatially homogeneous and isotropic universe, which imply strong symmetries in the solutions of Einstein's equations. So that's essentially that mathematics of made into English in this little sentence. So yeah, the main interest of Robertson's work is that he was the first to search in detail for all the mathematical models satisfying both not just homogeneous but an isotropic universe. And so this lays down the principles of the cosmological principle as it is now, which is at a sufficiently large enough distance the universe is both homogeneous and isotropic. So that's where that's coming from. In 1929, Hubble used the experimental data on the Doppler redshifts, mostly given by Slipher, who was not quoted, and found a linear velocity distance relationship, H equal V equals HR, with H being equal to 465 plus or minus 50 kilometers per second per megaparsec for 24 objects, and 513 plus or minus 60 kilometers per second per megaparsecs for 9 groups. The law was strictly identical to Lemaître's equation for 24, with almost the same proportionality factor, but Hubble did not make the link with expanding universe models. He stated the outstanding feature, however, is the possibility that the velocity-distance relation may represent the de Sitter effect. In fact, Hubble never read Lemaître's paper. he interpreted the galaxy redshifts as a pure Doppler effect due to a proper radial velocity of galaxies instead of as an effect of space expansion. And throughout his life, he would stay skeptical about the general relativistic interpretations of his observations. For instance, in the 202 pages of his book of 1936, The Realm of the Nebula, he tackled the theoretical interpretation of the observation only in a short ultimate paragraph on page 198, in which he quoted Einstein, De Sitter, Friedman, Robertson, Tolman, and Milne. As pointed out by his biographer G. Christopher, Hubble was chary. Chary? What does chary mean? Hang on a second. Here's a word I don't know. Chary. Cautiously or suspiciously reluctant to do something. Learn a new word every day. As pointed out by his biographer G. Christopher, Hubble was chary of all theories of cosmic expansion long after astronomers and physicists had been won over. When queried about the matter as late as 1937, he sounded like an incredulous schoolboy. Well, perhaps the nebulae are all receding in this peculiar manner, but the notion is rather startling. Indeed, the fact that the expansion of the universe was discovered by Hubble is a myth that was first propagated by his collaborator Hommensen as soon as 1931, and Hubble himself, who was fiercely territorial in a letter to De Sitter dated 21st of August 1930. He wrote, "I consider the velocity-distance relation, its formulation, testing, and confirmation, as a Mount Wilson contribution, and I am deeply concerned in its recognition as such." Now, I always thought it was due to the language barrier, but this is painting a more different picture. I always thought Hubble's law was Hubble's law, and not Lemaitre's law as it is, but I think it's more known now as Hubble-Lemaitre's law. But yeah, there's been this, I don't know what to call it, proportioning of who came up with which, and making sure each person has the appropriate amount of credentials. Share of glory, I guess, is probably the better term. Something I'm not really too. I think everyone should get the credit that they're due, and I mean, yeah, I'm walking straight into this. I'm going, right, I'm taking a large share of the lion's glory, and believe me, before the end, this is only the very beginning of what I've got to show. This is just like the tip of the iceberg. Below it gets a whole lot more interesting. A fractal universe is one full of life, and so is the superverse full of life. In showing the things that I have, and taking the artistic inspiration that I have, well, it gets very, very complicated. And I've got a bit of a tale to tell. I don't know how to vernacularize it. I'll get there eventually. But finishing this article, 1 month only after Hubble's article, Tolman joined the game of searching for an expansion of recession velocities, but still in the framework of a static solution. As he said, the correlation between distance and apparent radial velocity of the extra-galactic nebula obtained by Hubble and the recent measurement of the Doppler effect for a vast distant nebula made Humason at the Mount Wilson Observatory make it desirable to consider once more the theoretical relations between distance and Doppler effect, which he could be expected from the form of line element for the universe proposed by De Sitter. 1 year later, Tolman published another article where he suggested that the expansion was due to the conversion of matter into radiation, an idea already proposed by Lemaître in his 1927 article, who again was not quoted. A new opportunity for the recognition of Lemaître's model arose early in 1930. In January in London, a discussion between Eddington and De Sitter took place at a meeting of the Royal Astronomical Society. They did not know how to interpret the data on the recession velocities of galaxies. Eddington suggested that the problem could be due to the fact that only static models of the universe were hitherto considered. He nicely formulated the situation as follows: shall we put a little motion into Einstein's world of inert matter, or shall we put a little matter into De Sitter's Primeval mobile? And called for new searches in order to explain the recession velocities in terms of dynamical space models. Having read the report of the meeting of London, Lemaître understood that Eddington and De Sitter posed a problem which he had solved 3 years earlier. He thus wrote to Eddington to remind him about his communication of 1927 and request him to transmit a copy of De Sitter. Dear Professor Eddington, I have just read the February end degree of the Observatory and your suggestion of investigating non-statical and intermediary solutions between those of Einstein and De Sitter. I made these investigations 2 years ago. I consider a universe of curvature constant in space but increasing with time. I emphasize the existence of solution in which the motion of the nebula is always a receding one from time minus infinity to plus infinity. Lemaître precised, I had occasion to speak of the matter with Eddington 2 years ago. He told me that the theory was right and is all which needs to be done. That was not new, but had been considered by Friedman. He made critics against which he was obliged to withdraw, but that from the physical point of view, it was tout a abominable. Forgive my French. So I'm just trying to see. So I say, essentially, really, true credit for quite a lot of the ideas stem from Lemaître, including his idea of the primeval atom, which essentially is a neutron star. So Lemaître is a real genius, true genius. He just didn't know about the existence of neutron stars. The British astrophysicist was one of the most prominent figures of science at the time, and was in the best possible position to play a key role in the recognition of Lemaitre's results. This time he paid attention to Lemaitre's contribution, dispatched a copy of De Sitter in Holland, and H. Shapley in the United States. Eddington was somewhat embarrassed. According to Georges Lemaître, at the time a research student of Eddington, working with him on the stability of the Einstein static model, I remember the day when Eddington rather shamefacedly showed me a letter from Lemaitre, which reminded Eddington of the solution to the problem which Lemaitre had already given. Eddington confessed that although he had seen Lemaitre's paper in 1927, he had forgotten completely about it until that moment. On March 19th, Eddington accompanied his invoice of Lemaitre's paper to De Sitter in Leiden by the following comment: "It was the report of your remarks and mine at the Royal Astronomical Society which caused Lemaitre to write to me about it. At this time, one of my research students, McVitie, and I had been worrying at the problem and made considerable progress, so it was a blow to us to find it done much more completely by Lemaitre, a blow attenuated as far as I am concerned by the fact that Lemaitre was a student of mine." De Sitter answered Lemaitre very favourably in a letter dated March 25, 1930, and the Belgian physicist replied to him on April 5th. These letters are fully displayed in reference 43. In late May, De Sitter published a discussion about the expansion of the universe, which he wrote a dynamical solution of the equations for, with the line element phi 7 and the material energy tensor 6, is given by Dr. J. Lemaitre in a paper published in 1927, which had unfortunately escaped my notice until my attention was called to it by Professor Eddington a few weeks ago. On his side, Eddington reworked his communication to the following meeting of the Royal Astronomical Society in May to bring Lemaitre's work to the attention of the world. Then he published an important article in which he re-examined the Einstein static model and discovered that, like a pen balanced on its point, it was unstable. Any slight disturbance in the equilibrium would start the increase of the radius of the hypersphere. Thus he adopted Lemaitre's model of the expanding universe, which will be henceforth referred to as the Eddington-Lemaitre model, and calculated that the original size of the Einstein universe was about 1,200 million light years, of the same order of magnitude as the estimated by Lemaitre in 1927. Interestingly enough, Eddington also considered the possibility of an initial universe with a mass m greater or smaller than the mass me of the Einstein model, but he rejected the two solutions, arguing that m must be strictly greater than Einstein's mass. It seems to require a sudden and peculiar beginning of things, whereas for m strictly less than Einstein's mass for steady state, the date of the beginning of the universe is uncomfortably recent. Eventually, Eddington sponsored the English translation of the 1927 Lemaitre's article for publication in the monthly notices of the Royal Astronomical Society. Then, with the support of Eddington and De Sitter, Lemaitre suddenly rose to become a celebrated innovator of science. He was invited to London in order to take part in a meeting of the British Association on the relation between the physical universe, and spirituality. But in the meantime, he had considerably progressed in his investigation of relativistic cosmologies, and instead of promoting his model of 1927, he dared to propose the universe expanding from an initial point which he called the Primeval Atom. Then cosmology experienced a second paradigmatical shift. So a sort of paradigmatical shift. Say we go to Google. And you notice that it's all about who came up with which idea first. No, sorry. Rankings changed a wee bit, but I still hold number one. But as for the one that really counts, first, second, third, fourth, who dares wins. 4. The English translation of and discrepancies. A great deal has been written on the topic of who really discovered the expanding universe. The French astronomer Paul Goddard was probably the first one to rightly underline the priority of Lemaître over Hubble, and I agree. But since Lemaître himself never claimed any priority, the case was not much discussed. An intriguing discrepancy between the original French article and its English translation had already been quoted by various authors. The important paragraph discussing the observational data in equation 24, where Lemaître gave the relationship of proportionality between the recession velocity and the distance, in which the determination of the constant that later became known as Hubble's constant appears, was replaced by a single sentence. From a discussion of available data, we adopted r prime over r equal to 0,68 times 10 to the minus 20 centimeters per 20 centimeters. It was found curious that the crucial paragraphs assessing the Hubble law were dropped, so that either due to Eddington's blunder or some other mysterious reason, Lemaître was never recognized as the discoverer of the expansion of the universe. De facto, Lemaître was eclipsed, and multitudes of textbooks proclaim Hubble as the discoverer of the expanding universe, although Hubble himself never believed in such an explanation. I've still got to actually get my stuff into the actual astronomical journals, or whichever is the appropriate publication. So, yeah, there's my Achilles heel. But I can show a full academic record. Can you? Can you justify on the spot? Not like me. Not like me. Well, of course, you're a theoretical physicist. You're probably frothing out of the mouth going, my God, this guy knows nothing about general relativity. Oh my God, he knows nothing about cosmology. Which is quite rather true. It is. I try to base as I stand on the shoulders of Penrose and upon another particular cosmologist who's using an Einstein-Cartan formulation, which I particularly really go into go into. Unfortunately, names never always escape me, so I apologise for that. But providing me a mathematical framework on which I can build my idea upon, it's manna from heaven, because at least I've got some place to start within a mathematical framework. So essentially, a large part of my film is trying to show how to go about putting it into a mathematical framework. Yeah. So yeah, that's my Achilles heel. But let's do it collaboratively. I can show my academic record, and let us all take the appropriate glory for what it is. And believe me, there's so much glory to go around. Suddenly, in 2011, a burst of accusations had flared up against Hubble. From the suspicion that censorship was exerted either on Lemaitre by the editor of the MNRAS or on the editor by Hubble himself, suspicion based on the complex personality of Hubble, who strongly desired to be credited with determining the Hubble constant. So, in order to try and keep a record straight, this is why I do all my stuff as is. I'm doing my. So this is one motivation for this vlog. So it's all time and dated, making sure I leave enough big enough digital fingerprint across the internet. So it's not so easy. So I've been making sure that it's not so easy just to come along and nab it. The controversy was ended by Mario Levio from the Space Telescope Institute with the help of the archives, Lemaitre, Levouin, and the archives of the Royal Astronomical Society. Of course, you could always start up your own vlog and let's collaborate and we'll go from there. Yeah. It is not the scope of the present note to enter into the explanations that solve the conundrum. It is sufficient to say that it is now certain that Lemaitre himself translated his article, and that he chose to delete several paragraphs and notes without any external pressure. On the contrary, he was encouraged to add comments on the subject. But the Belgian scientists, who had indeed new ideas, preferred to publish them in a separate article published in the same issues of MNRAS. 62. What exactly is MNRAS? What is an acronym for? Who is he accusing of doing all the covering up? Monthly notes of the Royal Astronomical Society. I could see Hubble having persuasion in America, but the Royal Astronomical Society? Intriguing. For the present purpose, it is much more interesting to list in detail all the discrepancies. As far as we know, a little work that has never been done, in order to better understand how the preoccupations of Lemaitre had changed since 1927, and how the question which he had in mind in 1931 was less the expansion of space than the deep cause of it, how it started, and how the first galaxies could form. And so there we are. And if you want, I'm putting a link to this along with all the other various things that we've looked at over the course. If there's anything that really hits me from that article, is who crosses the finishing line first. first, second, third, fourth. Google the repository of all knowledge. I think I'm way out in front now. And that's the thing. The story there also shows just the community that was around Lemaitre and Einstein, Hubble. Of course, you talk about Minkowski, Einstein's former tutor, De Sitter. All these names. If you think about celebrities today, their names are not going to be remembered for very long. There'll be those ones that are truly legendary. But it's a thought that really gets to me. In 1,000 years, 2,000, 3,000, whose names are they going to say? Is it going to be yours? Because at the end of the day, this is ground zero for the Big Bang Kilonova hypothesis. And what do you want your story to be? I need help. Oh, I really do. And it's not just in the physics aspect. I'm trying to make a film. I'm trying to communicate this. How do we get this out to a large audience? I can only bring... How do you explain it to anyone? I try and start explaining this stuff to people, and it just goes like eyes blank, over the head. I don't know how to cross that much. I know how to talk about it from the point of view of everything I've come to know and learn. And of course, if you're a theoretical physicist and a cosmologist, you probably realize just how much I don't know. But at the same time, I've got to show up to the party. How can't you be? So please, what's your story going to be? Let's get a community going. Because in 1,000 years, it's going to be our names that they're going to be talking about. And I've got a vision. I want to show you Elon Musk's weakness. His Achilles heel. Before we go. I think it's probably this one. I particularly catalogue right. It's not that one. The name is Martin Tasmer. I think he may be the single greatest experimental physicist who ever lived. If his experiment can be reproduced. Elon, if you're watching this, please replicate this experiment. This is your Achilles heel. I want to invent the warp drive. And I've got frame dragging in a lab experiment. Not just, this is something mysterious. And I've got very specific reasons, which are going to be, and many of those reasons I'm going to be talking about in the forthcoming, next coming episode, as I continue on and making the film, because that's what I'm really driving at. There's a mystery in the rotation of liquid helium, and rotation is everything. It really is. It's where I had my great breakthrough, particularly seeing the Kermetric, and then seeing it in terms of a actual cosmological solution that can be mapped into a black black hole via the Einstein-Cartan formulation. But this is really where this essay was really where I kind of dig down into that and try and explore it as much as I can from what I know. But always my knowledge is growing and growing, and every part is wonderful. Of course, I feel the reality is a slightly little bit more different at the moment. But please come and join the community. And this is something I am truly grateful of. It's like I feel like I've just been handed the greatest prize in life can ever reward a person. I mean, and we need to build a community around it. So please come and join us and be part of living story of humanity. Until next time.